Okay, I'm going to try to get through about half of the next chapter, chapter 8. Let's make a slideshow. All right, so what are we looking at for the rest of the semester? We've got 2 chapters and 2 exams, 1 exam each. The last 2 chapters are on bonding, and there's so much material. I would split them into 2 exams. And we only have 1 more lab. I've given you the lab for next week, and after that, I don't have any other labs scheduled. So that begs the question, when is this report due? Okay, I think I've set up in the schedule. Did I put it in there? No, I didn't. Okay, so what's a reasonable due date for the last lab? Maybe I put it in this schedule. 18th of November. Let's see, what does that give you? That gives you 2 weeks. 18th of November for the last lab. We'll do that one next Tuesday, and then I think 2 weeks after that, we'll have the lab report will be due. Okay. So bonding. This is a topic that that plagued chemists for quite some time. We understood certain things about bonding, but we didn't have a coherent over an umbrella of understanding of what a chemical bond was. And I'm going to take it in roughly chronological order. I'm going to take the earliest simple explanations for bonding, and some of those concepts are still valid. But the questions that had to be considered were, what do we mean by a chemical bond? When you say a chemical bond, what does it actually mean? And we're going to answer these questions. Why do atoms bond with each other to form compounds? Why don't they just stay separate elements? How do atoms bond with each other to form compounds? So when they do bond, what's the process? What makes the bond form? We get our first indications, first steps, baby steps, into understanding the chemical bond with Dalton's atomic theory. Once we've accepted the idea that matter is made up of indivisible small parts, but that these what we call atoms are unique for each element, then we can start asking our questions, the questions above. Right. So there doesn't seem to be a simple definition for a chemical bond. I think we could probably come up with something, but it often depends on the nature of the reaction as to what we consider the chemical bond to be. We can say something as simple, as broad as a chemical bond is simply the force that holds atoms together. That seems to be a good place to start. And as a consequence, these atoms behave as a single unit. Now, sometimes those bonds form between 2 or more atoms, and that group moves about and behaves as if it's a separate unit, like a water molecule, for instance, or a carbon dioxide molecule. But sometimes atoms bond together in such a way that the size of the unit is variable. It can be this big, it can be monster. Those bonds are typically ionic. And we'll define what that means in just a second. One thing that we do know about the bond is that if we look at the energy content of the products versus the energy content of the reactants, the products are at a lower energy state. In other words, lower energy is more stable, and these atoms are always looking for stability. Right, we're trying to achieve the lowest possible energy state. Now, what we're going to learn is that low energy state can be an intermediate. The best example for that is nitroglycerin. When you make nitroglycerin, you combine the glycerol molecule, nitric acid, and some sulfuric acid, and you nitrate the alcohol groups on the glycerol molecule. And the energy, if we looked at that energy diagram as we proceed reaction from left to right, then you start off with reactants here. And the products might be, that needs to be much higher. You may end up over here eventually. But what happens is you go through a peak of energy to get the reaction to occur, and then it goes into a slump like this. And then there's a little hump over here, and it goes down. This is where your nitroglycerin occurs, right there. So on the local level, that's a lower energy state than this is what we call activation energy. But it's not the lowest energy state. That's why nitroglycerin is so unstable, right? You just look at it cross-eyed and it'll blow up. And that's one of the things that Alfred Nobel was trying to fix when he made dynamite. And he found that if he mixed nitroglycerin with kieselguhr, which is a diatomaceous earth, he could stabilize it and it would become useful. But that's what we mean by lower energy state. If it's lower than, actually, it should be lower than this. I kind of drew it, not to scale. But the idea still holds. Stability is given by lower energy. Now, when we get the interaction, the very simplest type of bond we're going to look at first is the ionic bond. And the reason we start with the ionic bond is because the force that holds two atoms together is purely electrostatic. And we have math formulas that will describe that interaction perfectly. In other words, when we have a singly charged sodium ion and a singly charged chloride ion, and we know the distance between them, we can calculate that force between them. We just use Coulomb's law, right? And if you haven't had physics, you won't be introduced to this. And there's a formatting error there. That little square between the J and the nanometer should be a dot. So that unit of measure is the joule nanometer. And that's a constant that's multiplied times the charge of one ion times the charge of the other one. And if one is a positive one and the other is a negative one, then we're going to come out with a negative number. And a negative number in this calculation means attraction. Positive number would be repulsion. But it wouldn't give us a bond either. And then the radius is the distance between the centers of the two ions. So if we know those values, we can calculate the force of that attraction. And it's very, very simple. In this case, the force would be 8.37 times 10 to the minus 19 joules per unit. 1 sodium, 1 chloride. Yeah, I already said that. Now, we can calculate the force of attraction for two ions in terms of Coulomb's law. But there are some molecules that are formed between identical atoms, right? That's the other end of the scale, where how do you account for that attraction? Because, right, they're not ions. They're identical atoms. So two hydrogen atoms gives us, right, throws a wrench in the gears. How do we deal with that bonding between these two hydrogens? Well, then we come up with the covalent bond. And this requires a transfer of electrons, whereas this is a sharing of electrons. So the concept here is that these two individual hydrogen atoms, when they approach one another, they find that, and it's useful to look at the interaction here as satisfying the electronic configuration of a noble gas. So if hydrogen wanted to look like a noble gas, which one would it go for? It'd go for helium, right? It'd have 2 electrons in that outer shell. That 1s2 would be a complete shell for hydrogen. And the way it's going to get it is to share an electron with another hydrogen atom. So one hydrogen atom, we're going to anthropomorphize here. The hydrogen atom on the left thinks it has 2 electrons. It's complete. The hydrogen atom on the right thinks it has 2 electrons. It thinks it's complete. Now, we didn't create any electrons. It's just the field is complete. And when they finally form the bond, that pattern of red dots is a probability distribution, right? Those are not individual electrons. Those are possible locations of the electrons. And notice that the electron density is greatest on axis between the hydrogen nuclei, or the protons, right? There's just one proton in it. Okay. So what we're looking for here is a balance, right? A balance between the repulsive forces, repulsion of protons, and this will scale to any atoms that are covalently bonded. We want a balance between the repulsion of protons and the attraction of protons and electrons from the neighbors. Okay. So there comes a point where these nuclei have an ideal distance between each other, the bond length. And that's the point at which you can't get the protons any closer because they push, and the proton-electron attraction is no longer strong enough to balance it. So you reach this ideal distance between the two. Excuse me. This is what it looks like on an energy diagram. So the best way to look at this one is, well, the nuclear distance in nanometers is on the x-axis, and the potential energy of the system is on the y-axis. And it's rather than we naturally look from left to right, but in this case, right to left is better, because on the right, the hydrogen atoms are far apart, right? And they have a certain energy, potential energy that we're calibrating to be zero when they're that far apart. Then as they approach one another, the potential energy drops. And at a given distance, in this case, 0.074 nanometers between the nuclei, you reach a minimum energy where that balance occurs. If you try to push them any closer, the energy required to get them closer goes way up. Okay? That's one of the obstacles to nuclear reactions. If you want to get the nuclei together, it takes a lot of energy and pressure. That's why in nature it only happens in stars. There's lots of gravity, lots of heat. So since we can't simulate the gravity on Earth in our devices that we're trying to build to capture nuclear fusion energy, we have to substitute heat. So at the center of the sun, it might be just a few dozen million degrees Celsius or Kelvin. In one of the devices called a tokamak, where they have a plasma that's confined by a magnetic field in a toroid, they have to go up over 100 million degrees to get that energy, enough energy to drive those nuclei together. Once you get them close enough, and the diagram doesn't get you that close, but once you get them close enough, then the repulsive effects are overcome by the strong nuclear force. And that draws those protons together and makes helium. Okay, but for our purposes, chemistry, we can't get them any closer. Okay? The ideal distance is that minimum energy. Come on. There we go. Okay, just to summarize, ionic bonding requires electron transfer. And if you look at the our original idea where we had sodium and chlorine, sodium has 11 protons, chlorine has 17, right? So it has 11 electrons and 17 electrons for chlorine when they're neutral. But if we transfer an electron from the metal to the nonmetal, and that's the way it always goes, the metal transfers an electron, right? So now we have 10 electrons here, and we have 18 electrons here, okay? So what's the electronic configuration for this one? 10 electrons makes it look like neon, and 18 electrons makes chlorine look like argon. Okay, so they're tending toward, I think we covered this before, didn't we? They're tending toward noble gas configurations. In either scenario. Okay, so ionic bonding requires transfer of electrons, and you produce a full, complete ion. Covalent bonding is a sharing of electrons. Now, like I've said before, nature just does what it does. We try to explain it. These are the categories that we've devised, ionic versus covalent. In reality, every bond, except where the atoms are identical, every bond has an ionic character, even if it's classified covalent. So you have a mix. There's a continuum between ionic and covalent, somewhere in between. And it depends largely on the electronegativity of the atoms. Okay, so the further apart they get on the periodic table, the greater the difference in their. Have we covered electronegativity? That's coming. Sorry. I'm using a term we haven't defined yet. Electronegativity. It's the tendency for an atom in the bond to draw electrons towards itself. right? So the bond may be covalent, but if one atom has a stronger pull on the electrons, then they tend to spend more time toward that other one. But not so much that they're complete transfer. It just, we say, it polarizes the bond. Maybe I need to move that slide up a little further and define my terms first. But you get a mix of ionic and covalent character for most bonds. Now, this polarity of the bond, we can say that the bond is nonpolar and covalent. We can never say nonpolar ionic. That's just a contradiction in terms. Nonpolar covalent means that there's roughly equal sharing of electrons in the bond. So the H2 bond would be a perfectly nonpolar covalent bond. Equal sharing. There's essentially no charge separation. Now we give a little bit with some bonds if they're very close together on the periodic table on this side, and I'll explain that in a minute. Polar covalent bonds are still covalent. They're sharing of electrons, but the difference in the pull, that electronegativity, the pull is great enough so that you do get a tendency for the electrons to spend more time toward the more electronegative atom. A good example of that one is hydrogen and fluorine. And we use a symbol. Sometimes we say this is slightly negative and this one's slightly positive. We use that delta to mean slight. It's not a complete transfer of charge. If it were that, then we'd have an ionic bond, and that'd mess with our theory. And also, we sometimes draw an arrow like this. That says this is toward the negative side, and that positive tail tells you which end is positive. So there are two ways of expressing this polarity. So we're implying an unequal sharing of electrons and a slight charge separation. Now this can be measured, right? Our example here is the hydrogen fluoride, and this has to be in gaseous state, similar to our electron affinities or what's the other one? I can't remember now. Ionization energy, there it is, where we use gases because we don't want anything phase changes to interfere. So this HF is a gas between two charged plates, and we can calibrate the instrument so that we know what the charge difference is between the two, and we can watch as we increase the charge. We can plot the response of the hydrogen fluoride in the gap. We can plot the response in a graph, and we can see where a peak is or a trough. I don't remember which one it is, but we can tell from that what actually is the polarity of the bond. We can measure it. Okay. So this is a summation. Chemical bond is the force that holds atoms together in groups so that they function as a unit. Now, why do they do this? They do this to minimize their overall energy. That's low energy means stability. Remember that thought for the second semester. How do atoms bond with each other? Well, they can either transfer electrons or they can share electrons. Okay. Electronegativity. Now we can get into the weeds on this one. Historically speaking, it came along actually not too long after Dalton's atomic theory by Berzelius. Have we mentioned Berzelius before? Berzelius was a Swedish chemist, I believe. And he was, well, as most of these guys were, they were brilliant. Berzelius is also known, he studied these phenomena and the nature of the chemical bond. He was responsible for things like the beaker. The tall beaker is called a Berzelius. So we've got the short ones that are about as tall as they are wide. There's one that he invented that's really tall. And he did that so that he could react things down here and there'd be less tendency to splatter out. They hit the walls and wouldn't get out. He did make some attempts to quantify the description of the chemical bond. The technology and the understanding at that time was lacking. But, I think, didn't Berzelius come up with I think he came up with the symbols for the elements. Yeah, I think he was responsible for that too. Okay. It took another 100 years of research and accumulated information for, I don't know what you'd call them. I think I've mentioned this before. If I haven't, then it bears repeating. Most scientists tend to be analytical. In other words, analytical comes from a Greek root, which means to tear apart. So you take things apart and see what they're made of. Every once in a while, you get a scientist who sees all those parts and pulls them together into a whole. They're synthetic thinkers. And Linus Pauling was one of those. He was a biochemist, I think. And he wrote a book called The Nature of the Chemical Bond and published it in the early 30s. And it explained so many things, it pulled things together so well that the Nobel Prize Committee in Chemistry awarded him a prize in 1954. That's characteristic of Nobel Prizes usually, or at least it has been in the past. It takes a decade or two to see if your work is worth the prize because it has to be vetted by other chemists over time. Now, recently, Nobel Prize committees have been a little lax in their standards. The most recent, of course, was Barack Obama's Peace Prize. He came into the presidency and did absolutely nothing to deserve it, but he got it anyway. That says more about the committee that awarded it to him than it does about him. Anyway, so Linus Pauling comes up with this idea and describes the nature of the chemical bond. And just parenthetically, he's the I don't think he was the only one, maybe two. Maybe two people got Nobel Prizes in two different categories. He was one of them. Okay, so in his description of the chemical bond, he was interested in this concept of electronegativity because he thought it helped explain how atoms attract one another, and then once they're bonded, how they behave in their bonded arrangement. So he devised the mathematics for calculating the electronegativity of every atom in the periodic chart And also remember that this is bonding the atom to a hydrogen, because hydrogen is the simplest. That's his point of reference. So when you bond them to hydrogen, then you can calculate an expected bond to energy, because we know the nature of hydrogen, and then we add these things to it. And we say that the expected bond energy is the hydrogen-hydrogen bond energy that is well known. And then we calculate the bond energy for an XX molecule, whatever that happens to be. And we can do that, right? How much energy do we have to put into that molecule in the gaseous state to break it apart? And we can measure it. Add those together and divide by 2. That's the expected bond energy for an HX bond. Okay. And put in parentheses there, this is oversimplified, right? There's a lot more that goes into this calculation than we have time, and I don't have the expertise to explain it anyway. So once we get this expected bond energy, then we can actually take the molecule where hydrogen is bonded to that atom and experimentally determine its actual bond energy. And if we take that and subtract the expected one, we get this difference, the difference in the, and that delta is an indicator of the electronegativities. And the calculation of the electronegativities, which is, I mean, it's not, he just didn't pull it full blown out of his head, right? It's based upon calculations. But the system is set up so that once we know what that difference is, and we can assign a number to each one of the elements, then we can compare them. Right? Once we have an electronegativity value for an element, then all we have to do is say if 2 elements are bonded together, we just subtract the lower one from the higher one, and that gives us a value that we can compare to other values and say, all right, where's the dividing line from nonpolar and polar? And that's what we do. But first we have to know what those electronegativities are. And if we draw our periodic table again, come over here like this, like that, and up here like that. And there's hydrogen, and there's helium. Okay, and we have our noble gases, and we have fluorine up here, and we have way down here in the lower corner, I think we're just going to stop at cesium. The trend is for electronegativities, that is, the higher the value of electronegativity, the more strongly the element in a bonded situation pulls on the electrons. So the higher the number, the stronger the pull. And the strongest pull is fluorine with 4.0. So if you go from left to right in a period, the electronegativity increases. Electronegativity increases. And if you go from bottom to top, it also increases. Okay. Now the reason for that is, well, let's see, cesium, it gave us 0.7. Okay, so our range is 0.7 to 4. The reason that so the trend is lower left to upper right, kind of like ionization energies. And for similar reasons. Let's see, do I have it in black and white? No, everything's on that slide. Okay, so from left to right, we're in the same period. The electrons are all in the same energy level. We're adding electrons, but each time we add an electron, we add a proton. So we're increasing the effective nuclear charge as we go from left to right. And that contributes a larger pull on electrons from left to right, because all those electrons are in the same energy level that we're adding, right? The valence, the period number. So we're increasing that positive charge, and that has an increasing pull on electrons around them. If it's just the element, then yeah, it pulls on those, but it also has a pull on the electrons that are in the bond. Okay. Now this one, as we were to go down, we would be increasing, adding electrons out to larger orbits. And we'd be adding more protons also. But the ones we're adding to the outside don't feel the positive pull as strongly because they're shielded by these negative charges underneath. So as we go down and we get bigger orbitals, the effective electronegativity decreases. So overall, lower left to upper right, we're increasing electronegativity. Okay, and these numbers are on the Pauling scale. And that's the most commonly used. There are other scales, right? But we effectively use them the same way, regardless of what scale you're in. Notice that the trend is reasonably consistent for the representative elements. Remember, these two and these 6 groups. Once you get into the transition elements, they tend to still go up to a point, and then they drop off until you get to the representative elements, and then they pick up again. And that has to do with the nature of the d orbitals and the way they fill and the way they behave. So those are a little squirrely. It's kind of like a roller coaster in there. So if lithium and fluorine react, which has more attraction for an electron? Where's lithium? Lithium's way over there, fluorine's way over here, all in the same period. So fluorine would have the greater attraction. If a bond between fluorine and iodine is formed, which has more attraction? Well, fluorine is high here, and iodine is down here. So fluorine again would have the greater attraction. Okay. All right, and I already explained why. And there we go. Lower left to upper right. Oh, I do have an explanation. So there it is in print. Takes a little more room for the groups than it does for the periods. Okay, so where is the dividing line? When you have a difference between electronegativities. When you take the electronegativities and subtract them, where's the dividing line? Well, if the electronegativity is less than or equal to 0.2, right? From 0 to 0.2, we say that's non-polar covalent. Definitely. No variability at all. If we go from now 0.3 up to 1.4, is it, I think? Yeah, 1.4. This would be still covalent, but this is polar covalent. And anything over 1.4 is ionic. Now there's some argument depending on whether it's I think up to 1.2 in here. If we had 1.2 to 1.4, then it would still be polar covalent if it was non-metal. But if it was non-metal, then it would be considered ionic. That's not in the graph, is it? Greater than 1.5. Oh, excuse me. 1.5. 1.4 is covered there. There we go. And what we're saying is that even if we make this differentiation in here, we've still got, except for this one instance, we've still got some ionic character in any of those covalent bonds. All right. Let's see if we can arrange these. Let's make some room here. Now we're gonna qualitatively arrange these, or semi-quantitative. We're not going to actually use the electronegativities to get our answers. Let's see how much time. Should look back. There it is. 350. Okay. Arrange the following bonds from most polar to least polar. Well, I don't think these. So what do we have? We have, for the first one, we have nitrogen and fluorine, oxygen and carbon, oxygen and fluorine, carbon and fluorine. Okay. So the nice thing about this one is they're all bonded to fluorine. So all we have to do is from most polar to least polar is the most polar is going to be the ones that are furthest apart from each other on the periodic table. So let's see, nitrogen and fluorine is two-way, oxygen is closest. So this one is going to be the least polar, right? And then nitrogen would be the next one. And then carbon and fluorine would be the furthest apart. Okay, so most polar to least polar. Let's see, carbon, nitrogen, oxygen. Okay, we got that. Okay, how about B? Now we got a mixture. Carbon, fluorine, nitrogen, oxygen, and silicon, fluorine. Yep. Okay, from most to least polar. So silicon and fluorine are pretty far apart, actually. And then the next farthest would be carbon and fluorine. And the closest in this list would be nitrogen and oxygen. Right next door neighbors. Okay. Oops. And then C. We've got a completely non-polar bond. We've got boron and chlorine. And we've got sulfur and chlorine. And notice that the covalent bonds are between only nonmetals. We don't have covalent bonds between metals and nonmetals. Now there's another bond that we haven't introduced. It's called the metallic bond. We may talk about that a little bit in this, or I can't remember. It could be in the second semester. Okay, the most polar. Well, we know the least polar is going to be this. And then furthest apart, boron and chlorine. Probably this one. And then left over is sulfur and chlorine. Would be close enough. There we go. Okay. So we came to conclusions that are probably right. If we had the actual numbers, then we could justify that. Okay. Next question. I'll leave that up there. We're actually going to use numbers in this case. So we want to find the least polar, yet still being polar covalent. So we've got this magnesium and oxygen, carbon, oxygen, 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 and silicon oxygen, and nitrogen oxygen. Okay. The way to answer this question is to work backwards. Still considered polar covalent. So which ones would be covalent? Not that one. That's a metal and a non-metal, right? So that one's out. The rest one are considered, but polar covalent. That one can't be polar because they're identical atoms. So now all we have to do is arrange these. Least polar, yet still considered polar covalent. Okay, least polar. So carbon, oxygen are, there's a nitrogen in between. Silicon, oxygen, they're further apart. And nitrogen and oxygen are right next door to each other. Least polar would be that one. And we can justify that with calculations, right? Nitrogen's 3 and oxygen's 3.5. So that difference is 0.5. Silicon is 1.8 and oxygen is 3, right? No, 3.5. Yeah, 3.5, 1.8 for silicon. So that's 1.7. Okay, talk about that in a minute. Carbon and oxygen. Okay, so oxygen is still 3.5 and carbon is 2.5. So there we have 1.0. Okay, nitrogen and oxygen, 0.5 puts that in the polar covalent range. That one's good. I'm going to skip to carbon, oxygen, and get back to silicon in a minute. This one puts it in polar covalent also, but it's a greater number than nitrogen, oxygen. 1.7 is the sticking. That says it's ionic. But the problem is that silicon's a nonmetal in this bond, silicon and oxygen. That's when you have two nonmetals together, you have the covalent bond. So this is kind of a sticking point here, 1.7. I think it depends on what author you go to as to where the breaking line is. We could make this breaking line 1.7 instead of 1.5, and that'd solve the problem. But if it is covalent, it's extremely polar. And I think it is covalent based upon what I know about its use. The silicon-oxygen bond is used in cases where it can't be ionic. If it were ionic, it wouldn't function the way it's supposed to in those applications. So, but the question was the least polar covalent. And for that, we're okay. Most polar without being considered ionic. Maybe we are going to consider this ionic. That's a big question. Right? Maybe because silicon is one of the metalloids. Right? Sometimes it acts like a metal, sometimes a non-metal. Maybe this is the case where it acts like a metal. Yeah. So to answer that question, we go to this one. The most polar without being ionic. And based on the information that we were given, then that's the only conclusion we can make. Okay, what do we mean by dipole moment? Moment is a term borrowed from physics. Moment implies a directional force. So if we have, if I'm pulling, if I got a rope attached to a big weight and it's sitting on the floor and I'm pulling on it, then the moment of that pull is at an angle because it's down there and I'm pulling on the rope this way. So I'm pulling with a certain force in this direction. Now, we're not going to go into a whole lot of detail with this one yet, but in physics, you can take that pull and you can create two, and I had the word on the tip of my tongue, two vectors that can be split off from that in the horizontal and the vertical direction. Right? So if it's going to move this direction, I want to know how much of that pull is directed here. It's not the same amount, it's less, right? Because some of it is vertical pull, some of it is horizontal pull. But the dipole moment tells us how much that is and what direction it's in. So for molecules, the dipole moment is an expression of the difference in charge, whether it's complete ionic or whether it's, and usually when we say dipole moment, we're talking about covalent. Because the dipole moment of an ionic bond is very simple, right? It's just that Coulombic equation. So, and that arrow that we drew like this, that's how we express the dipole moment. Typically what we have here is, if it's a short arrow, it's a weak dipole moment in that direction. And if it's a long arrow, we're implying a stronger dipole moment or a difference in electronegativities. Okay, points to the negative charge with the positive tail on the positive end. Okay, now up to this point, we've talked about the polarity of individual bonds. But we want to eventually get to the point where we can talk about the polarity of the entire molecule. So covalent molecules behave as single units, whereas ionics are not really molecules. Ionics are an array of positive and negative charges. Right? So when you spill salt on a tabletop and look at it in a magnifying glass, which I'm sure none of you have done, it's rare for my students to have done that. What you see is little cubes. That's a clue to the ionic structure of that compound. Right? You have an array of sodium and chlorine ions. Right? That sodium will be surrounded on all three dimensions with chlorine ions, and then the chlorines are surrounded by sodiums. It's a network of sodium and chlorine chloride ions. So we don't talk about those in terms of molecules. If we have to say what's the ratio, then we would say 1 to 1, right? Rather than 3 billion to 3 billion. 1 to 1 is simpler. And then if we have a molar mass for an ionic compound, we're talking about the simplest ratio of positive to negative charges. So we would have a value like 23 and 3545 for this would give you that one. Or if you had, say, ammonium phosphate, right, we would have to have 3 here. And we would calculate an ionic, a formula unit mass for that one. But when we talk about molecules, these are covalently bound atoms that behave as a single unit, right? Now, they can form arrays if we cool them down enough, like water, right? We can freeze water and it will form a regular arrangement of water molecules. But you've still got the individually covalently bound atoms in each molecule. Whereas that's not the case with ionic compounds. So I went off on that tangent trying to describe the need to understand how these molecules interact with one another. And we're going to get into that in a whole lot more detail later. Let's see, are we going to do it this semester? Possibly. Yeah, yes, we are. Okay, I just remembered. So what we want to know is, how does the molecules behave in terms of their polarities? We can say something about the bonds in terms of each bond polarity, but what does it take? What do we need to know in order to describe the polarity of the entire molecule, or even parts of the molecule? You need two factors. One is polar bonds. You need to know something about the bond polarity. Right? Are the bonds in the molecule polar? If they're not, then the entire molecule is nonpolar, right? It's got nothing to feed off of to make it polar. But if the bonds are polar, then we need to know geometry. How are those bonds arranged in space, and what is the vector sum of their polarities? So, example, if we have two oxygens, right, like that, you'll learn how to do that in a minute. That there's no polarity there. Or if we have let's see, water. Water has this shape. Okay. Oxygen is more electronegative than hydrogen. So the dipole moment on each bond is toward the oxygen. Okay. So what we want to do is sum those vectors for the whole molecule. And there's a way to do that. I mean, since you haven't had physics, we won't go into a lot of detail. But in effect, the whole molecule has a dipole moment in that direction. So on this side of the molecule, it's slightly negative, and on this side, it's slightly positive. So we can say that based upon the bond polarity and the geometry of the molecule is polar. If we had something like this, carbon dioxide, and this is the molecule, carbon dioxide, it's linear, right? It has polar bonds that direction and this direction, but notice that they're identical. So they cancel each other out, and this is non-polar because of the geometry. Even though we have polar bonds, the geometry tells us that overall the molecule is non-polar. Those are the two factors that you need to determine the polarity of a molecule. Oh, there's water. Now, we can say one molecule is polar and one's non-polar, and if we find another molecule that's polar, there may be differences because of the difference of the atoms to which they're bound and the geometries. So we're speaking in general terms here, except for this one. This is essentially non-polar, but you're still drawing electron density away from the center, and you're making this end slightly negative and the center slightly positive. So overall, we're saying that the molecule is nonpolar, so that contributes to its behavior, but still, the electrons still do what they do, right? So we've got negative ends here. What that means is that when these molecules approach one another, say it's pure carbon dioxide, when they approach one another, how are they going to bond if they form some intermolecular attraction? Well, it's difficult to get at that positive because we've got all this around here, right? Even though this is slightly negative and that's slightly positive, you can't get another molecule of carbon dioxide close enough to have a strong attraction. So that tells you that it behaves as if it were essentially nonpolar. But if we had something small like this, and the molecule we know is polar, then this proton, which is really small, can get in really close to its neighbor, right, and form a really strong attraction there. That's known as a hydrogen bond. We'll talk about that in a minute. Right, there's your carbon dioxide. And you see from the color densities that you still have that distribution of electrons toward the oxygens, but they're equal and opposite. So they cancel one another out for the whole molecule. All right. So I want to say a word about regular geometries, regular shapes. These will be our starting points when we try to talk about the shapes of molecules. Right. If you have something like carbon dioxide, that's a linear shape. Right. So if we go from this carbon to these oxygens, the bond angle here is 180 degrees. That's characteristic of a linear molecule. Okay. If we have a central atom of some kind, let's say boron trichloride, trihydride. Let's do that one. The regular shape for that molecule is called, let's see, this is linear. This is trigonal planar. Right? It forms an equilateral triangle. If you draw an imaginary connection here, like that, that's where you get your equilateral triangle. Now, the molecule itself has these bonds here. These are not bonds. This is a visualization of the shape. Okay, trigonal planar. If you have something like methane, CH4, then you're going to have like this and one in the back. That is a bond there. Hydrogen here, hydrogen there, hydrogen there, hydrogen there. And we can form this trigonal base and then pull it together, and we find that we have a trigonal pyramid, which in geometric terms is a tetrahedron. That's the regular shape for that type of molecule with a central atom and 4 attached units. Okay. Now, this bond angle here, remember, all the way around is what, 360 degrees? So each one of these would be 120 degrees bond angle. Okay. Bond angle here is a little trickier. For tetrahedrons, if it's regular, then the bond angle between this one, that one, and this one, or this one and that one, any of them, is nominally 109.5 degrees. I just memorized that one. I mean, there's a proof for it, but I think it's simpler just to memorize it. We'll talk about others, right? You can go to where you have 5, we call them ligands, 5 ligands on the central atom versus 4, 6 ligands, and that's where we stop. But we'll get to those in just a minute, or maybe next. Yeah, that may be next time we meet, Thursday. We mentioned this earlier. Stable compounds tend to have noble gas configurations for their respective atoms. If they come from the second and third periods. With that, you don't have interference from electrons in d orbitals. D orbitals really mess things up. So as long as you're here, then, or you can tend toward that, this noble gas or that noble gas or that noble gas, then you're in better shape. So potassium and calcium then would lose electrons to end up here. But we're still in the second third. That's known as the octet rule. Now, there are exceptions to the noble gas rule. Usually in period 4 and above, because now we're getting into d orbitals and they can exceed the octet. Right? And we'll talk about that more probably next week. You can also have fewer than the octet in some cases. And when we say that it can exceed the octet or it can be less than the octet, these are based on real compounds. Right? We're not making this stuff up. So it's like I say before, nature just does what it does. And when we find these compounds, we got to explain them. Okay. So the most common, now we're going to look at, try to explain the most common ions that would form for these metals. And to do that, we're going to look at representative elements. I think we're going to stick to this side. And we're going to look at the most common ions. For 10, the most common ions would be 2 plus and 4 plus. That's experimental evidence. So if we draw 10 in terms of its electronic configuration, we would start with krypton in both cases. And that would take up 36. And this would have how many protons? Where is it? 50. And then we would have a 5s2 and a 4d10. I'm going to start with neutral atoms, and then I'm going to make the ions first. And then we would come over 10 would be 5p2. Okay. So how do we make this ion? Right. What are the valence electrons in these molecules? These, right? The highest number here. So you have 2 here and 2 there. If we remove 2 of those electrons, this is a metal, right? If it gives up those electrons, which metals, that's what metals do. If it gives up those electrons, that unbalances toward 2 plus. Okay. If it gives up 2 more from its highest valence, right? Then that would make it 4 plus. So that's an explanation for what we're trying to do here. What we're tending toward noble gas configuration, and we're not getting there. But these are the highest energy orbitals, and we can take 2 away and make that one, take 4 away and make that one. What we're trying to do is explain why is it 2 plus and 4 plus. And if we look at its neighbor, lead, it's going to have 6s and 6p with 2 and 2. So lead is also going to be a +2 or a +4. Okay. Then if we go next door to bismuth, right? Now we have 2 s's, 6s and 6p3. So it would tend to have a 3 plus or a 5 plus charge. And that's what we find for bismuth. Thallium, that's Tl. Okay, thallium is 6s2 and 6p1. So we'd lose 1 p electron, make it a +1, or we'd lose the other 2 s's and make it a +3. Let me see. Where is my? I have a division, a stopping criminal here built in. Trying to see.
53,
53.
I think.
Yeah, there it is. Okay. Okay, we've got time. I can probably get there. That way, if I can get to that dividing point, then we won't have to rush on Thursday. All right. When two nonmetals react to form a covalent bond, they share electrons in a way that completes the valence electron configurations of both atoms. When we say completes the valence, that is, they tend toward noble gas configuration. When a nonmetal and a representative group metal react to form binary ionic compounds, the ions form so that the valence electron configurations of the non-metal and the metal tend toward noble gases. So you still have that noble gas tendency. Only with ionic compounds, you actually do transfer electrons and you get the true electronic configuration of noble gas for both the cation and the anion. Whereas with nonmetals, when they form the covalent bonds, it's sort of imaginary. Right? They think they look like noble gases. So we come up with isoelectronic series. Have we talked about isoelectronics? Isoelectronic series, it's a big name, and it just means that these species have the same electronic configuration, each one. And what we've chosen here is, if you see a noble gas in a series that's supposed to be an isoelectronic, that means the rest of them should look like that noble gas. So neon, if we look at neon, and then we go to the left and add one electron, that looks like neon. If we go to the left and add two electrons, oxygen looks like neon. If we go down one, if we swing back around to the next period, sodium would lose one electron to look like neon. Magnesium would lose two electrons to look like neon. And aluminum would lose three electrons to look like neon. So they all have the neon configuration. All right. I'm not going to take a lot of time with this. It's fairly simple, right? If you want a noble gas configuration in an alkaline metal, an alkaline earth, and a halogen, just pick one of those noble gases and then go to the left for your halogen and add one electron. Go to the right, down to the next period, add one for the alkaline metal, add two for the alkaline earth. Subtract. Subtract one for the alkaline metal to make a positive one, and subtract two for the alkaline earth to make a positive two, and you've got your isoelectronic series. Here's an example. Right? And each one is going to look like that. They're going to have complete outer shells. They're going to have the same number of electrons, but they're going to have different number of protons, right? Because you can't change the number of protons without changing the element. So each one of these is going to retain its protons, but it's got the same number of electrons. Okay. So we've talked about atomic size, radius. We sort of inferred ionic radius when we looked at what happens to an ion when you add an electron or subtract an electron. We've talked about ionization energies, electron configurations. We know those. We can predict formulas for ionic compounds, right, based upon where they are in the periodic table and how they interact with one another, balance the charges. We've been doing that since we learned to name compounds. And we can rank bond polarities. Okay. So let's stop for a moment and look at binary ionic compounds like sodium chloride or calcium fluoride or I don't know, rubidium bromide. As long as you've got metal and non-metal, you're talking about ionic compounds. We want a handle on how strong these cations and anions are bound together. And one of the indicators of that is called the lattice energy. So we have to define what we mean by lattice energy. We start with separate gaseous ions. So for instance, let's take it really simple. Sodium gas plus chloride gas. They come together and they form the sodium chloride solid. So which way is energy going to go for that? Is it going to be exothermic or endothermic? Which side's more stable? Let's look at it that way. That side's more stable. Right? So it's going to give up energy because this is lower energy. It's going to give up a massive amount of energy. And that's the lattice energy that we're talking about. Actually, let's see. Let me see how they define it. The change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. Okay, so it will be a positive value. Excuse me, a negative value, exothermic. That energy is leaving the system. So lattice energy will be negative. And this is related to the Coulomb's law. K happens to be a proportionality constant, and I think K is experimentally determined, so we're not going to worry about it too much because it's going to depend on the compound that's being formed. But we will have a short distance between the ions, and we'll have difference in charge between the two. Now, if we want to know the energy of formation for that compound, remember the formula that we used. We want to end up over here, right? And we want to know the energy of formation. The way to determine that is you start from the most stable at room temperature and pressure for sodium, which is a solid. And the most stable for chlorine is diatomic, and that's a gas. Yeah, that's a gas. Then you adjust the coefficients to give you that formula. So this one's fine, just like it is. And this one needs to be 1/2. So if we wanted to know the enthalpy of formation, the delta HF under standard conditions, then that's the formula we're working for. And remember, Hess's law, where you can combine equations, right, to get the final. So we want to take these equations, we want to look at them, what actually happens in this process, and separate those equations out. And then we can recombine them to get this one. And this would be one of them. Right? But how do we get here? How do we go from here to here in steps? Well, first of all, you've got to form this into a gas, right? That's the sublimation of the solid. So the sublimation energy would go the other direction. We just have to reverse the sign to go that direction. So we'd have to put energy in here. Then we would have to ionize it to make the sodium ion. So that's the ionization energy, right? We know we can find that in a reference manual. Then we would go to this one, right? First thing we'd have to do is break the bond between those two. It's already a gas, so all we have to do is break the bond. Right? That's the dissociation of the nonmetal. And then we would ionize it, which would be not the ionization energy, but the electron affinity, because it's going to accept an electron. That's an exothermic process. And then we would put those two together, right? We would put those two gaseous ions together to make the solid, and that, they don't name it there, but that is the lattice energy. And if we added all those together, using Hess's law, we would get the value for this equation. All right, that's just a graphical representation of what we've done in the process. The one on the left is magnesium oxide. The one on the right is a completely different one. That's sodium fluoride. You don't have to spend a lot of time on that. Just recognize that we can take the individual steps, add them all together, and they can give us the whole. So here's an example. If we want to know the formation, the energy of formation for lithium fluoride, then we write that equation, and then we take the individuals and we say, all right, what's the enthalpy of sublimation? Well, if we go from a solid to a gas, we have to put energy in. The sublimation would be a positive 161 when it goes from a gas to a solid. But if we go the other direction, we just change the sign. So that requires 161 kilojoules in, no, that's not right. We have to change the sign eventually because the negative is exothermic. And if we go from a solid to gas, that's endothermic. Right? So that could be confusing if you don't pay attention to the signs. Ionization of the lithium, that's first ionization energy. And that does require an input of 520 kilojoules. And that one has to be a positive value also. Okay, then we go to the fluorine. Right, we're going to break the fluorine bond. Right? And since we have a half a molecule, instead of 154 kilojoules, it's 77 kilojoules because we only need a half of them. Okay, then we form the ion, right? The electron affinity, and then we get the lattice energy as 1,047 kilojoules per mole. Now this graphical puts them together, and we find that the overall change is 617 kilojoules to go from the individual most stable elements to the compound. Okay. Lithium fluoride, that's the one we just did, isn't it? Okay. So notice here they did change the signs. Right, 161, 520, change the signs. Didn't need to change the signs on these because they're in the right order. Then when we add them all together, we find out that this process from the solid lithium and the gaseous fluorine to the solid lithium fluoride gives up 617 kilojoules per mole of lithium fluoride. There we go. Okay, I mentioned before the ionic character of covalent bonds. The way we measure that, as long as the X and the Y atoms are not identical, then we can measure a dipole moment, right? With that device I showed you with hydrogen fluoride, you can measure that dipole moment. You can also calculate the dipole moment based upon what you would expect the ions to do when they attract one another, and that would involve Coulomb. Then compare those two, ratio them, and that will give you a percent ionic character. If we do that for each of these different representative molecules, we find that the electronegativity difference is the breaking line is roughly 1.5. I think that's where they got that number. Lithium iodide is right on the line. And since lithium is a metal and iodine is a nonmetal, I think lithium iodide is a ionic compound. But it does have some covalent character because its percent ionic character is only about 51 or 2. Right? So the rest of that is covalent character. Whereas the ones in blue are more covalent than they are ionic. Right? And the extremely, let's see, the highest percent ionic character is lithium fluoride. Lithium over there, fluorine over here. Now, why is it not cesium fluoride? Because they're further apart. Well, cesium fluoride is has a greater electronegativity difference, but when we do that calculation, the ionic character is higher for lithium fluoride. And I think that's largely due to the fact that lithium is a very small ion, and it can get really close. So the closer you are, the stronger the pull. Remember that ratio of Q1 and Q2 over R, right? So the closer they get, the stronger the force. And when the ions are really small, you can get them close together. Okay. Now here's an operationally defined ionic compound. If you can put the ionic compound in solution, or you can melt it, one or the other, right? If it's soluble in water, fine. If it's not, then you can melt it, right? A solid ionic compound is an insulator, an electrical insulator. Well, it's a thermal insulator too. Why? Because those ions are locked in place in the solid. They can't move. And if they can't move, they can't conduct the current across. So that's why a big cube of salt, put a battery on one side, a lead on the other, and hook it to a light, the ions can't move. But if you melt it, then the ions can move and you can conduct current. That's one definition for an ionic compound, one that will conduct an electric current, whether it's melted or in solution, as long as you can separate those ions. Okay. So we talked about models. And models are applied to theories, not laws. Laws just say what happens under these limited conditions. But if we have a theory, we're trying to explain why, we need a model, because a model can be modified to see what happens to the theory. All right. Our model is a macroscopic view of the microscopic world. If it's a physical model, that works well. Like in my organic chemistry class, we'll have models where we put usually carbon and some other things together, string them together and make models that you can see, so that you can rotate them in space and you see how they interact with one another. That's a model. But you can also have mathematical models that describe what's going on. And sometimes that's the only way you can model a system, especially if it has more than 3 dimensions. Well, if we include time as 4 dimensions. Right. So if we have a model that's trying to describe, in our case, let's restrict it to the chemical bond. Our model, we have to recognize first and foremost that the model is not reality. The model is a representation of reality. And as a consequence, rule 2, or exception 2 is models are oversimplifications. Right? What we have to do is we typically include in a model the major factors that are operating in the theory that we're trying to model. And the minor factors, we sort of shove those aside until they get in the way. And as a consequence, oversimplifying the model means that under many circumstances, it turns out to be wrong. And over time, typically what happens, models are modified. They become more complicated as they age. And remember, did I explain what you do when a theory fails? Yeah, what happens when a theory fails? And this applies to models too. When a theory fails, theory failure, what do? Well, this one says you modify. You modify it, so it'll take into account those problems. If you can identify what the problems are, then modify the theory, and it broadens its application, right? Or you can restrict its application. In other words, you can say, this model doesn't work outside these parameters. And that's what we do in physics with Newtonian or classical physics. Generally speaking, it has to do with the size of objects and how fast they're moving. So under a large number of parameters, Newtonian physics works fine. But if you get really, really huge, like black holes, then you need relativity. Or if you're trying to during an eclipse, see, is gravity having an effect on light? Does it bend light? And that experiment was performed. Yeah, it does. It confirmed Einstein's prediction that light would bend around the sun during an eclipse. So that needs relativity. Or if you get really, really, really small, then you need quantum mechanics. Right? So restrict the application as the best you can do right now. Your third option is to start over. Just throw it out and start over, right? And the model of the atom, the plum pudding model, remember that, where you had the electrons were these particles and the pudding was the positive charge, right? And Rutherford's experiment blew that one out of the water, so we started over. We threw plum pudding out and we went to the nuclear model. And then the fourth one, which is you won't see anywhere else, is you turn your theory into a religion. You just believe it, have no evidence for it. And that's global climate change and Darwinism, two of the major theories that have no basis in fact. Now, I'd get arguments, about that from the faithful. But that's why I don't argue with them. Okay, let's see, where were we? Fourth, we must understand that the underlying assumptions in a model, we have to understand the assumptions so that we don't abuse the model, right? We don't make it say something that it's not supposed to say. It's not intended to say. And this is the good news. When a model turns out to be wrong, we often learn much more than when it was right. Because if we can understand why it went wrong, then that gives us a clue to what's actually happening at the microscopic level. Oh, here it is. All right, so restrict the model's application. I put that one first. Modify it. All right. Throw the model out, start over. And there's your example. I left out the religion part. As far as Darwinism goes, Darwin didn't put it in his published works, But in a letter to a friend, he admitted to being a good scientist. He said, if these things are not found in the next so many years, then my theory falls apart. And what he was talking about was the fossil record. If we don't find infinitesimally small changes in the fossil record to show to justify his theory, then that theory just falls apart. And as a matter of fact, we haven't found them. So Darwin wouldn't agree with his theory now either, but there are devotees that still cling. Okay, bond energies. What do we mean by a bond energy? The energy required to break a bond. How much energy must be added to the system in order to break the bond? So those energy terms are always positive values. When you see a list of bond energies, and I'm going to show you one in a second, and you probably see it on your printouts. Those values are always positive because in order to identify bond energies, they are positive input values. I guess we'll get to it in a minute if I don't talk too long. Okay, so a single bond. So our hydrogen single bond had one electron from hydrogen coming together with an electron from the other hydrogen to make a single bond. And that line, that single bond, represents 2 electrons. If we have a situation like this for oxygen, then we have a double bond, and that's 4 electrons. Okay? If we have something like this, nitrogen, that's 6 electrons. 2 electrons for each bond. A bond is always 2 electrons. Now, what happens to the bond length and the bond energy? The bond length will be a certain distance here. I think it was 0.074 nanometers. This bond distance will be, let's see, bond length. Decreases as you add bonds. It's not linear, right? We're going to learn about that probably next semester. Maybe this semester. So you don't get this one to be half the distance of that one, and this one to be a third the distance of that one. They do get closer, but it's not a linear change. And the bond energies, this direction, increase. Right? So this is a stronger bond than the double bond, and the double is stronger than the single bond. And those increases are not linear also. Okay. Okay, so here's your list of, bond energies. Right? And those are in terms, probably kilojoules per mole, I think. Kilojoules per mole of bonds. So there's the hydrogen at 432. Remember, these are all positive values because we're taking that bond and we're putting energy in to break the bond. So they're all going to be positive. And what can we do with those bond energies? Well, that comes up next. Let's see. So the same amount of energy when these hydrogen atoms, if these individual hydrogen atoms, neutral atoms, come together, they will give up the same amount of energy that it took to break the bond in the first place. Now, if we want to calculate the overall enthalpy of a reaction, right, for a given reaction, what we need to know is the energy required to break the bonds minus the energy released when the new bonds are formed. So example. Say we have hydrogen and oxygen gas forms water. And we're going to keep it simple, water gas. What bonds? Well, let's balance it first. Let's see, this is 2, that's 2, and this is 2. Okay. So what bonds are broken here? Well, the bonds broken here are single hydrogens. The bonds broken here are double bonds. And the bonds formed here are 2 oxygen-hydrogen bonds, right, for each one of the waters. So if we say how much energy goes into breaking the bonds, how much do we have to put in, right? So this is a positive input for these. Well, we got to do it for 2 of these. So whatever this is times 2. Right, we can go back. 432. Right? And then we add how much energy does it take to break that oxygen double bond, which would be 495. There's only one of those. Okay. We put that in. Then since the energy is coming out, we subtract. Right? So we subtract the energy coming out, and this would be an oxygen hydrogen, which is 467. But how many bonds actually form? 1, 2, 3, 4, because you got 2 of them. So that would be 4. So we take these together, subtract those, and the reason it's in this order is because those values are always positive. Well, there's another example. But if we add these together and subtract those, then we'll get the delta H for this reaction. And it's very, very accurate. If you actually determine this enthalpy of this reaction in the laboratory, you come out very close to that calculated value. Okay, this example is easier than it looks. And the reason for that is, look at the molecule. What are the similarities between the molecules? The left, the reactant, and the product. CH3 on both sides. So those are a wash. You don't have to do the CH3, right? Because it's the same on both sides. So what we have to do is the comparison between carbon nitrogen single bond, right? It's going to be this. It's going to be this, these. Then you're going to have on this side, you're going to have a nitrogen and triple bond to the carbon. And on this side, you're going to have these, right? These are the wash. Then we're going to have this carbon bonded here and this one here. Well, actually, these are a wash here. And this one is a wash because it's the same bond. So the only one we have to do is the carbon nitrogen bond. 305 minus carbon 347. Right? What is that? Let's see, that's 2, 4 minus 42 kilojoules. Okay. Now you can do it the long way, but I think it's a lot of extra work. Okay, time to pause. We'll come back on Thursday and finish this chapter. And that way, we'll have time for next week's lab before we go in the lab to talk about it like we have been doing. All right.